Okay, let's talk about matrices. What are matrices? So before going into matrices, let's see what is transformation. First of all, let's try to understand transformation. So transformation is nothing but when we are changing a vector from one to another. For example, we have a vector in a vector, and let's see, now if it's finished, this is transformed into another vector. Let's say this one a dash. So that's called transformation. This is the transformed vector. A transformation can also represent the whole space. So when we apply transformation, the complete space is transformed. The complete space is transformed. That means all the lines, all the vectors will get transformed. For example, if we have, let's say, a square in here. So after applying transformation, all these lines of the square will be transformed. Like this vector gets transformed, the same will happen to this. So what is linear transformation? So for transformation to be linear, it must follow two things. First is that all the lines must remain lines. That means if let's say if we have let's say we have some shape, let's say we have this in our coordinate axis, and after applying the transformation, these lines must remain lines. Well, it doesn't look like a line, but let me try to make a square in here. So this line must remain a line. After transformation, whatever the transformation we are applying, it cannot be a curve like this. After applying the transformation, it cannot be a curve. It must remain the line, whether we are rotating it or whatever we are doing this. So it must remain the line. So or lines. So lines must remain lines. Second thing that transformation must follow to be linear is the origin should remain same. The origin, it should remain same. It should remain at the same place. We cannot, after applying the transformation, we cannot shift the origin to other place. Origin should remain same. Or instead of these 2 points, we can also simply say that the grid lines of the space must remain parallel and evenly spaced. For example, if we have this coordinate axis and we can draw the grid lines like this, even after applying the transformation, let's say we are applying a transformation which does something like this to the space. Let's say this thing happens. So these lines must remain parallel even after transformation. These grid lines must remain parallel. And for example, these lines, they are still parallel and they are still evenly spaced. The space between them is still the same. So if this thing is maintained, we can say our transformation is linear. There are many applications of linear transformation. For example, in computer graphics, images are rotated. If we have, let's say, an image like this, and after applying a transformation, we can rotate this image like that. So similarly, we have something share. We can apply share transformation on it. So this image will look, after applying the share transformation, it will look like something this. Coming back to the matrices, a linear transformation can be expressed in form of a matrix multiplication. Now let's say we have a vector A, and the unit vectors are, let's say, I cap, I1 cap, and J1 cap. Now after applying the transformation, let's say we are applying the transformation. Okay, so after applying the transformation, let's say we are rotating the space. So this A vector now will look something like this. Let's say it's a B vector now, and this J1 will, if we see this, it will be rotated just 90 degree in anti-clockwise direction, and this J1 will be here now, and this I1 cap will be here now. Let's call it I2 cap now, and this one as J2 cap. So we have rotated it 90 degree in anti-clockwise direction. Now then I1 cap becomes I2 cap, and J1 cap becomes J2 cap, and our matrix A vector becomes B vector. This whole transformation that we have done can be expressed in form of a matrix multiplication. Let's try to see that. Let's say we okay, so let's take the matrix A, This is the matrix that's actually doing the job, and this is called the rotation matrix. We can see that the I1 was uh, has the x component of 0 and y component has x component of 1 and y component of 0, and the I2 now has x component of 0 and y component of 1. Similarly, the J1 cap had x component of 0, it had an x component of 0 and a y component of 1. And after transformation, we have J2 cap, which has y component of, if we see, it has a y component of, y component of 0 and an x component of -1. So our I unit vector rotated transformed from this to this, and our J unit vector transformed from this to this. So we can see the rotation matrix that we are applying here has these two vectors here and here. So this is where our I landed, this is where our J landed. This is where our I landed, and this is where our J landed, J cap landed. So our B vector is A vector, A matrix dot A vector. So we are applying the rotation transformation on A, and we are getting B. We are getting B. That's what we have written here. So our transformation matrix is 0 minus 1, 1, 0, and let's say the x component of A vector is A1 and the y component is A2. So we can write it like this. We will take A1 of the first column of matrix A and A2 of the second column of matrix A. So after addition, we will get our B vector, which will have minus A2 as our x component and A1 as our y component. So there are some other examples of transformation matrices. For example, we have a matrix, say B 1 1 0 1 1 1 0. So this matrix is actually applying a shear transformation on the vectors. For example, if we have a space with I cap here, J cap here, after applying this B transformation, we will get something like this. Now let's talk about order of a matrix. Order of matrix. So if we have a matrix with n number of rows, these rows we have n number of rows and m number of columns. Let's say these are n and columns are m. So we say the order is n by m. So if both n and m are equal, then it is a square matrix. That implies it's a square matrix. Both square as well as non-square matrices can actually represent a linear transformation. Now let's quickly try to understand what happens when we multiply matrix with a matrix and a matrix with a vector. First of all, let's see what happens when we apply matrix with a vector. Matrix vector multiplication that we're talking about. Okay, so let's take for example, we have a matrix which has order of 2 by 3 and a vector of order 3 by 1, which has 3 rows and 1 column. And after applying the multiplication, we get another vector which we know will have 2 rows and 1 column. So what is actually happening when we do this matrix vector multiplication? So actually, we can see this is a vector which has 3 components, x, y, and z. It's actually a 3D space. It's a vector in a 3D space, and this is a vector in a 2D space. It has only 2 rows. So it's a vector in a 2D space. So this matrix is a transformation which is transforming a vector from 3D space to a 2D space. But what about matrix multiplication? Now let's see what happens at matrix multiplication. So the concept here is simple, like in composition of a function. When we apply a function into a function, it's a composition of a function. This is similar. The matrix multiplication is similar to that. For example, if we have a vector and we apply a transformation matrix B to it, we will get a vector, let's say U. Now, if we apply another transformation matrix to this U vector, let's say A, we will get a final vector. So we are applying first B transformation, then we are applying A transformation. So we can simply write it like this, applying transformations to the vector v, and as we know, the matrix multiplication follows the associative rule, so we can multiply first these two matrices and we will get a matrix which will, this matrix is the matrix multiplication of A and B. See how matrix multiplication is done. So let's say instead of A we have 1 0 2 1 0, and for B we have 1 minus 2 1 and 0, and for vector v, let's think we have x and y, x component and y component. Let's try to multiply A, this is A, this is B, and this is v vector. So let's try to multiply A and B. For to multiply, what we do is we take the row, we take the row of this matrix and multiply it with the column of B matrix. So it will be like, take this, multiply it with by this, and add it with 2 times 1, 2 times 1. So we are taking this row and this column. And now for the second element of the matrix C, we will take this row again and multiply it with this column. So it will be 0 times minus 2 plus 2 times 0, 2 times 0, 2 times 0, and 0 times minus 2. So now for this element, we will multiply this row with this column. So it will be 1 times 1 plus 0 times 1. And for this element, we will multiply this row with this column, and it will be 1 times minus 2 plus 0 times 0. So we will get final matrix as 2. This will be 0, this will be 1, and this will be minus 2. That's how multiplication is done. We take for first element, which is 1 element of first row and first column, we take the first row of the first matrix A and multiply it with the first column of matrix B to get the first row to get the first element at the first row and the first column. Similarly, for the element at first row and the second column, we will take the first row of A and multiply it with the second column of B, so on. Make sure when we are doing the matrix multiplication, as I have already done here, as I already told you here, that the order, for example, if the order of A is m by n and B is n by, let's say, k, we have to make sure that these two must match. They must match. Then only we can perform matrix multiplication. The resultant will have an order of m and k, m by k. Now let's talk about matrix addition. Matrix addition. For matrix addition, first of all, it is equivalent to, as we do in functions, it's like adding two functions. Now, for addition to be done, for example, if we have matrix 1 and we have matrix 2 and we want to add these two matrices must have the same order. If this has an order of, let's say, n by m, this must also have a same order for these two matrices to be added. Otherwise, we can't perform addition on two matrices. Now, the sum is calculated. The sum is calculated by just simply adding the corresponding elements. For example, the first element of this with the first element of this, we will get the first element of this. Similarly, this one on adding with this one, we will get this one, and so on. There are some important properties on matrix addition. The first one, let's say properties. Let's talk about properties now. The first property is commutative property. So it says if we have a matrix M1 and we add it with matrix M2, we can also add just swap it. We can add M2 with M1. It's one and the same thing. But on multiplication, this rule doesn't apply. We cannot say M1 times M2 is same as M2 times M1. It's not same. Keep that in mind. So the second property of matrix addition is associative. So associativity. What it says, if we have a matrix, let's say M1 and M2 and M3, and we can actually add M2 and M3 first and then add the resultant of these with M1, or we can add M1 and M2 first and add the resultant of these two, addition of these two with M3, and the final result of both these will be same. Another property is distributive property. Distributive, it says if we have a matrix, let's say M2, and we had M2 and M3, and we can multiply the resultant of these with this M1, and we can simply write it M1 multiplication with m2 plus m1 multiplication with m3 will be done on from left side or from right side. By that I mean this is the distribution can also, if we have a let's say multiplication from this side, we can also distribute it. But this is not same. I mean, it will be it's from left side and it's right side, and we know AB is not equal to B in matrix multiplication. But they're not same, but we can apply the distribution. We can distribute M1 to M2 and M3 from here as well. And we have to make sure to write M2 and M1 in this order. We cannot write M1 and M2 like this. Now, if we have a matrix multiplication A and B, and we are multiplying this new matrix with scalar x. Now, what we can do is we can simply multiply this scalar x with A and then multiply this new matrix with B. Or we can also have to multiply this. This is also same as if you multiply this scalar with B first and then multiply the resultant with A.